Good morning and welcome to this short presentation of my PhD thesis for the BNCTAM Best Thesis Award 2015. Currently, when it comes to designing innovative vehicles, the four following adjectives are of utmost importance. They must be fun, smart, intuitive, and green. Let me exemplify this. If we take a look at the self-driving car, one can say that this is pretty fun. Innovative vehicles are also smart and intuitive. For example, we can see that vehicles are embedded with sensors that enable us to regulate the speed and to prevent collision with others. When considering the green adjectives, improvements have been realized by using alternative propulsion systems. The plug-in hybrid car is a very nice example. However, in order to better protect the environment and to reduce the energy consumption, there is no secret. It's necessary to reduce the mass of the vehicle. A recent report indicated that a mass reduction of 100 kilograms leads to a reduction of 6 grams of CO2 per kilometer.
The design of modern vehicles is carried out in a computer-aided engineering CAE framework. This approach relies on numerical tools such as computer-aided design, computational fluid dynamic, stress analysis, crash simulation, etc. All these numerical tools predict the behavior of the vehicle or parts of it and aim at designing it at a moderate cost. Indeed, the expensive fabrication of prototypes is limited to a few in an advanced design phase. Let us now consider that the multibody system analysis team detects that the dynamic response of the vehicle is not as expected. The reason is that the upper suspension arm is too weak. As a result, the analysis team asked the structural optimization team to improve the arm stiffness while keeping the same mass. To perform the structural optimization problem, the concerned component is isolated from the mechanical system, and some load cases as well as boundary conditions are selected. This selection is essential and is generally guided by the designer experience. However, since these few load cases can hardly represent the whole dynamic loading, iterations between the two teams are usually needed, which slows down the design process and lessens its efficiency.
In this research, we wanted to replace the traditional component-based approach that leads to this iterative process. To achieve this, we want to extend structural optimization techniques to account for dynamic loadings as the ones encountered in multibody application. In other words, we want to supersede the component-based approach by a system-based approach in which we perform an integrated optimization of flexible components within a multibody system approach.
The optimal design of multibody systems is a very complex task, and it is not a simple extension of structural optimization techniques. The interactions between the flexible components plus significant couplings between vibration and component inertial properties result in complex design problems and leads to convergence difficulties if not treated properly.
In order to solve this challenging design problem, we adopted a rational, meticulous, and intelligent approach toward the formulation and the solution of multibody system optimization problem. We started from the classical optimization framework and we deeply revisited each step. As we can see on this figure, we can identify four different parts: the model parameterization, the multibody system analysis, the sensitivity analysis, and the numerical optimization. The model parameterization is a very important step because it defines the potential of the optimizer to minimize or maximize the objective function, but also it determines the complexity of the optimization problem. Indeed, this step defines the design variables that will be subsequently modified by the optimization process. Here, we need a suitable parameterization that is adapted to the complex design of multibody system. This means that we want to have a limited number of design variables, we want to be able to deeply modify the geometry, we want to have a CAD description of the geometry, and we want to avoid mesh distortion issues. These characteristics do not fit with standard type of structural optimization. Therefore, we developed a new approach based on a level set description of the geometry that gathers this characteristic. The level set description of the geometry is an implicit representation of boundaries. Let me illustrate this parameterization on a small example. We would like to introduce a circular hole in a square plate. To introduce a hole, we define a scalar function based on cat entities, that is, the level set function. Here, the level set function is based on a superellipse. Afterwards, we can merge the two elements, and based on the level set function values, we can define the material, the void, and the boundary. Considering the optimization process, we can modify the shape of the component by changing the level set parameters, or we can modify the topology of the component by adding or combining several level set functions. Concerning the multibody system analysis, the second step of the loop, we focused on a nonlinear finite element approach. We adopted this formulation because it is totally general and it can be used to analyze complex multibody systems as illustrated by the following examples. Moreover, this finite element formalisms is well suited to perform advanced optimization problems. Let's now move on to the optimization part. In this thesis, we investigated two methods to solve the multibody system optimization problem. We named them the fully coupled method and the weakly coupled method. The fully coupled method incorporates the time response coming directly from the multibody system simulation. On the optimization flowchart of this method, we can see that the multibody system analysis and the numerical optimization work in an integrated manner. Since the optimization problem considers directly the time response, we solve a dynamic response optimization problem. I will now focus on two important points related to this method. First, we investigated and pointed out several formulations of the optimization problem in order to have good convergence properties. Indeed, it turned out that the formulation is a key point to solve that type of problem because it has a strong impact on the design space. Another point I want to mention is the sensitivity analysis. This step can become extremely CPU time consuming when considering a dynamic response optimization problem. Indeed, we need to compute the derivative of the displacement, velocities, and accelerations for all the time steps of the simulation. Here, by revisiting the sensitivity analysis of multibody system, we propose an efficient approach to compute all these derivatives by reusing the data that we have already computed during the multibody system analysis. In contrast to the fully coupled method, there is the weakly coupled method. This method reformulates and decouples the problem using a two-step approach. Firstly, a multibody system simulation is performed, and secondly, based on the result of the multibody system simulation, a series of equivalent static load cases are defined that are then used in the optimization process. This method is interesting because it transforms the complex design problem into a static response optimization problem, whereupon all the standard techniques of optimization can be employed. However, this method has been developed for a particular type of multibody system formalism that is tailored to this method. In this thesis, we developed a method to compute the equivalent static load cases adapted to nonlinear finite element formalisms. We demonstrated that this method is efficient and that it leads to a more integrated method where a more complex optimization problem can be considered. To close the loop, we have demonstrated that both methods, the fully and the weakly coupled method, can converge toward the same optimized design. The development of this thesis has been validated on industrial applications. We optimized some powertrain component in collaboration with Tech Thorsen and Toyota, where we obtained impressive mass reduction up to 30%. I will conclude by the fact that this thesis paved the way for future developments, some of which have already started. An example is the coupled problem between structural optimization and optimal control. This presentation focused on automotive application, but the scope of this thesis is larger, and the developed method can be employed for the application such as electric motors, robots, biomechanisms, and so on. The developed method can also consider higher frequency domain for which we can, for example, control the noise radiated by the system, I hope you enjoyed the presentation and thank you for watching it.